Hello, my dear students. Very good morning to all of you. Today we will discuss about the semiconductor material. As per the before class, already we have discussed about the types of solids like conductor, insulator, semiconductor. Out of these three materials, basically conductors are used for electrical device construction. Insulators are used for constructing outer cover or base of different devices, and semiconductor metal is our today's focus. Basically, semiconductor mostly used in electronics component manufacturing or electronics devices manufacturing. So let us start details some fundamental points about the semiconductor materials. So semiconductor fundamentals. First of all, we have to discuss some important points or fundamental points about the semiconductor material. Mostly, what is semiconductor? First of all, we have to know what is semiconductor. Semiconductor is one type of material which has both conductor property and insulator property. That means it can allow current flow or may not allow current flow. It has mixing property. That is why the name is semiconductor. Not completely insulator or not completely the conductor. Mixing property. But that mixing property never happening simultaneously. Basically, at certain condition like at absolute zero temperature, it can act as an insulator. But at above absolute temperature, it can be act as a conductor. This type of metal which has the mixing property of a conductor and an insulator, these materials most important examples are germanium and silicon. Though so many metals are available, but most fundamental examples are the germanium and silicon. Basically, those metals are under the semiconductor group all have the 4 valence electrons. 4 valence electrons means if we study the electronic configuration of semiconductor material, its outer cover carry 4 electrons. Valence electrons means outermost electrons are known as the valence electrons. And in case of semiconductor, always we get equal to 4 valence electrons. That may be germanium or may be silicon. Basically, this semiconductor material has resistance property and conductance property. If we study the resistance property and conductance property of the semiconductor, these two property lies in between the conductor and insulator. What is the meaning? Lies between the conductor and insulator means in case of conductor, your resistance is very low. And in case of insulator, your resistance is very high. But in case of semiconductor, your resistance is not as low as in conductor or not as high as in semiconductor. Its resistance is more than the resistance of conductor, but less than the resistance offered by the insulator. That is why we can write or we can tell the resistance properties lies in between the conductor and insulator. Similarly, the conductance property. Conductance property for conductor is very high because conductor allows current flow through it very easily. So accordingly, conductance property of conductor is very high. But the conductance property of insulator is very low and may be assumed as zero, no current flow. The conductance means current flowing property. So in case of conductor, conductance is very high, but in case of in case of insulator, the conductance is very low or we can consider as the zero. But if we consider the semiconductor, this property lies in between the conductor and insulator. Conductance property of semiconductor is not as high as in conductor or not as low as in insulator. So that is why the resistance and conductance properties lies in between the conductor and insulator. Then if since the semiconductor definition is it may allow or may not allow the current flow, or it shows the conductor property and insulator property, accordingly, so when we get some current flow through the semiconductor, we can get the current flow due to two types of charge carrier. In case of semiconductor, we can get current flow due to two types of charge carrier. One is named as the holes and another is named as the free electrons. Holes are the positive charge particles and free electrons are the negative charge particles. So we can get current flow due to both these two types of charge carriers in case of semiconductor, which is not valid for the conductor and insulator. If we consider the conductor case, we can get the current flow only due to free electrons. And if we consider the insulator, then we can take the current is 0, so accordingly no free electron and no holes. Then this type of material is specially used for manufacturing the electronic devices like diode, transistor, different types of ICs, and so many devices. Even digital device also consisting of the semiconductor materials. Another fundamental feature of semiconductor is its energy band diagram. Energy band diagram. So energy band diagram of semiconductor, if we see properly, actually in case of semiconductor, the forbidden energy gap value is very low, not 0 as in conductor and not very high as in insulator. In case of insulator, we can get around 13 or 15 eV gap, forbidden energy gap. But in case of semiconductor, that energy gap is 1.1 eV, which is a very small value, and we can convert the semiconductor to conductor by overcoming this gap by putting some impurities. So if we study the energy band diagram of a semiconductor, it's a valence band and conduction band. Valence band is basically consisting of valence electrons and conduction band is consisting of due to free electrons. The energy band possessed by the free electrons is known as the conduction band and the energy band possessed by the valence electrons are known as the valence band. And the gap between the conduction band and valence band is known as the forbidden energy gap. These three definitions are same for all types of materials. But if we focus on the semiconductor material, basically this gap is very small, which is around 1.1 eV. And this forbidden energy gap practically indicates the electrical conductivity property of any material. If this gap is very high for any material, that going towards the insulator property. If any material has this value very small, then that proceeding towards the conductor property. But in case of semiconductor, this is 1.1 eV, which is a very small value and proceeding just approximating towards the conductor property. So accordingly, it is very easy to convert the semiconductor to insulator putting some materials. Next, we consider the classification of semiconductor. This semiconductor is broadly classified into two classes. One is named as the intrinsic semiconductor, another is known as the extrinsic semiconductor. So, intrinsic semiconductor. In the pure semiconductor is basically known as the intrinsic semiconductor. When we consider the pure germanium or pure silicon, then that is known as the intrinsic semiconductor. But when we add some impurity or some extra material with the pure semiconductor, then that type of semiconductor is known as the extrinsic semiconductor. So out of these two semiconductors, Practically, intrinsic semiconductor is not used for manufacturing any electronic devices due to some demerits, because intrinsic semiconductor has a demerit, it has not so high conductivity, and also at absolute zero it may be insulator, but at above absolute zero temperature, though it can convert it to conductor, but its conductivity is not so high, which is not usable in practical cases. So that is why to increase the conductivity of the semiconductor, some impurities are added. Some special type of impurities are selected and added with the pure semiconductor. And when we add the extra material, then we get the extrinsic semiconductor. That extrinsic semiconductor practically used for manufacturing the electronic devices. Out of the two types of semiconductor, let us discuss some important features of intrinsic semiconductor. First of all, we have to know what is intrinsic semiconductor. Basically, the semiconductor in the purest form is known as the intrinsic semiconductor. Purest, completely pure form. No addition of any extra material. Pure germanium or pure silicon. These two are the fundamental examples. Then if we consider the basic property of the intrinsic semiconductor, basically its resistance and conductance property. Most important electrical property is resistance and conductance property. So these two property lies in between conductor and insulator, as we already have discussed in before slide. So resistance and conductance property lies in between conductor and insulator. Then if we consider its temperature effect property, basically the semiconductor shows negative temperature coefficient of resistance. Negative temperature coefficient of resistance means if temperature increases, then resistance decreases. If temperature decreases, its resistance increases. Due to this property of the semiconductor, we can consider to be converted, semiconductor can be converted to conductor. Let us see, when temperature increases, its resistance decreases. This indicates resistance decreases means it can be converted to conductor. Less resistance means eligible for the current conduction. So this implies at higher temperature, its resistance decreases, automatically conductance increases, or current flowing capability increases. Current flowing capability increases means it can be acting as a conductor. Similarly, if temperature decreases, resistance increases. Resistance means current opposing property. So if resistance increases, then current flow property or conductance property decreases. Resistance high means current flow capability less. Current flow capability less means conductance less. So that is going towards the insulator property. So this point indicates semiconductor's capability of acting as a conductor and insulator. That is why we have to try how we can use the semiconductor to convert to conducting material. So due to this temperature effect, suppose we use the intrinsic semiconductor directly for manufacturing any devices. Keeping in mind this temperature effect. Simply controlling the temperature, we use this material as the conductor or as the insulator. But practically that is not good. Always we have to keep in mind our controlling of our temperature. So that is why temperature point of view, to convert the semiconductor to conductor, keeping in mind the temperature is not a suitable method. To convert the semiconductor to conductor, we have to use some extra techniques. Temperature property we can use, but temperature को using the temperature and controlling the temperature, intrinsic material is not used directly for manufacturing any device. So accordingly, we have to consider about the extrinsic semiconductor. So before considering the extrinsic semiconductor, another point now we discuss why rejecting the intrinsic semiconductor for manufacturing any electronic devices or any electrical devices. So let us consider this atomic structure of intrinsic semiconductor. If we see the atomic structure of intrinsic semiconductor considering the silicon here, then basically all the atoms of silicon are engaged in covalent bonding. Atoms are basically engaged in covalent bonding. So covalent bonding means sharing of electrons. We know each atom of semiconductor has 4 valence electrons. So each atom has 4 valence electrons. First of all, consider the central silicon. It has 4 valence electrons. These 4 valence electrons are making 4 complete covalent bond with 4 silicon atoms. Now the central silicon atom is engaged in covalent bonding with 4 silicon atoms. This one and this one are 4 complete covalent bond. Similarly, each silicon atom also engaged in 4 covalent bonding, and accordingly we are getting the intrinsic semiconductor piece. So overall, covalent bonding is involved in. So no free electrons are available here. All the valence electrons are engaged in covalent bonding. If we take any piece of intrinsic semiconductor, initially we can see all the atoms are engaged in the covalent bonding, no availability of the free electrons. But for getting the free electrons, we can increase the temperature or we can apply some external electrical supply. When we apply some external electrical supply or increase the temperature, what will happen? Some of the, not all, very few number of the covalent bond will break. Suppose this covalent bond will break. When the covalent bond will break, we get one free electron. So since very few number of free covalent bond may break, so very few number of free electrons we get. But in this case, the number once any covalent bond will break and we get a free electron means behind it will leave one vacant place. That vacant place is known as the generation of holes. That means in case of intrinsic semiconductor, if by chance any covalent bond will break, the number of free electron is equal to number of holes. Due to breakage of covalent bonding, the generation of number of holes will be equal to the number of free electrons. And that will be very few number. Due to this few number of charge carrier generation, the conductivity may not be very high. So this cannot be used for manufacturing any devices directly. So this is the reason, and that is why we have to consider the extrinsic semiconductor in manufacturing the devices. So let us discuss about the extrinsic semiconductor, which is the main important semiconductor material. Extrinsic semiconductor, first of all, we have to discuss some important points about the extrinsic semiconductors. What is extrinsic semiconductor? Basically, extrinsic semiconductor is the impure semiconductor. The pure semiconductor is known as the intrinsic, but that pure is not so good property for any device manufacturing. That is, in case of gold, the pure is very important one and also very meritorious one. But in case of semiconductor, the pure word is not so good for the electrical part. Though extrinsic semiconductor is the impure semiconductor, this one is the good for the electrical conductivity. So impure semiconductor means something may be mixed with the semiconductor. Basically, with the pure semiconductor, some impurity materials are added to get the extrinsic semiconductor. And there are some special impurity materials named as the trivalent material and pentavalent material. Trivalent material means the materials having 3 valence electrons in their atoms. For example, gallium, indium, these are the trivalent materials. Then pentavalent material means the materials having 5 valence electrons in their atoms. For example, arsenic, antimony, these are the pentavalent materials. So for getting the extrinsic semiconductor, either we can take the pure semiconductor plus pentavalent impurity, or we can take the pure semiconductor plus trivalent impurity. At a time, both cannot be added. You have to add either pentavalent impurity with the pure semiconductor for getting the extrinsic semiconductor, or you have to add the trivalent impurity to get the extrinsic semiconductor. So accordingly, 2 special types of impurities are added. That is, one is named as pentavalent, another is known as trivalent. Then next we have to know one important point. The process of adding this impurity with the pure semiconductor. There is a special process, not mixed as usual in normal way. That process is basically named as the doping. The process of adding impurity is known as the doping. Then next we consider what will happen if we added the impurity. Till time we clear, when we add some impurity with a pure semiconductor, we get extrinsic semiconductor. And the special types of impurities are pentavalent impurity and trivalent impurities. The pentavalent impurity examples are arsenic, antimony, and the trivalent impurities are gallium and indium. But next we consider why we are adding, what will be the effect after adding. Actually, when you add the pentavalent impurity or the trivalent impurity, the conductivity of the semiconductor increases highly as compared to the intrinsic level. In case of intrinsic, the conductivity value, and after adding the impurity, if you check the conductivity value. So due to addition of impurities, the conductivity increases highly. Current flowing capability will be good. Then, if we add the pentavalent impurity, suppose we add the pentavalent impurity, then we get the extrinsic semiconductor. But pentavalent impurity addition increases the number of holes. Number of free electrons. Addition of pentavalent impurity with a pure semiconductor increases the number of free electrons. What is the meaning? Suppose in case of intrinsic semiconductor, we take a piece of intrinsic semiconductor and let us consider this intrinsic semiconductor has 10 number of holes and 10 number of free electrons. Because in intrinsic level, equal number of free electron and a hole. When you add the pentavalent impurity, the number of hole will be as usual, but the number of free electron will increase. Similarly, if you consider the trivalent addition, the number of holes will increase, but the number of free electron will be as usual as in case of intrinsic level. So accordingly, due to addition of impurities, the conductivity of the semiconductor increases. And how the conductivity increases? Because the addition of impurity increases the number of charge carriers. Basically, pentavalent increases the number of free electron charge carriers, and the addition of trivalent impurity increases the number of full charge carriers. Then, Since two types of addition is possible, accordingly, extrinsic semiconductor is of two types. One is named as the P type, another is known as the N type semiconductor. So, since after adding the pentavalent impurity, the number of free electrons increases, accordingly, these pentavalent impurities are known as the donor impurities, because pentavalent impurities donate some extra free electrons to the intrinsic semiconductor. When we add or when we consider the intrinsic and pentavalent, intrinsic level, in case of intrinsic level, equal number of free electron holes. But when you add the pentavalent impurity will donate some extra free electrons. So accordingly, free electron number will be more. So this impurity is also named as the pentavalent donor impurities. Similarly, when you consider the intrinsic semiconductor, equal number of free electron holes. But when we add the trivalent, the number of holes will increase. Holes means missing of free electrons. That means here generation of holes means accepting level of free electrons is more. No donation. Accepting level is more. Accordingly, the trivalent impurity is known as the acceptor impurities. Why the pentavalent is known as donor and why the trivalent is known as the acceptor, we can be very clear in forward slide while we are considering the atomic structure of P type and N type. So, as per the basic features of extrinsic semiconductor, this is one impure semiconductor and two types of impurities we can add. One is known as pentavalent, another is known as trivalent. Then, due to addition of impurities, conductivity increases. Then, due to addition of a pentavalent, free electron charge carrier increases, and due to addition of trivalent, whole charge carrier increases, and pentavalent is known as the donor impurity, trivalent is known as the acceptor impurity. So based on these two types of impurities, extrinsic is of two types. One is known as P type, another is known as the N type semiconductor. This is the basic features of extrinsic semiconductor. From the structure, one single arsenic atom has 5 valence electrons, and out of 5 valence electrons, 4 is making 4 complete covalent bond, and the 5th valence electron is not making any covalent bond with any germanium atoms. So accordingly, this 5th electron will be free, and it is one free electron. So now it is clear that due to addition of one arsenic impurity atom, we get one extra free electrons. So if we add a small piece of arsenic atom, and if the small piece of arsenic atom carry the million or billions of arsenic atom, so we get million or billions of extra free electrons. Accordingly, due to addition of pentavalent, now we get large number of free electron generation. P-type semiconductor. When you add the trivalent impurity with the pure semiconductor, you get the P-type semiconductor. Due to addition of this trivalent impurity, the number of holes will increase. Large number of holes will be generated. So let us see how holes are generated in this case. Suppose we consider some pure semiconductor like germanium here. So let us consider one trivalent impurity, that is gallium. We can take also indium. So we know gallium has 3 valence electrons. So these 3 valence electrons of gallium will make 3 complete covalent bond with 3 germanium atoms. But the 4th covalent bond is incomplete. This covalent bond is requiring 1 electron, or in the position of accepting 1 electron. That means your gallium atom is in the position of accepting electron from outside. This accepting of 1 electron is same as the missing of 1 electron. missing of one electron is the same as the generation of one hole. So hole means that is a missing of electrons. So in this covalent bond, there is a missing of electron means, or there is a position of accepting one electron means generation of holes. So it is clear that due to addition of one gallium atom, we are getting one hole generation. So if we add a small piece of a gallium, we get million or billions of extra holes. So accordingly, due to addition of trivalent impurity, you are getting large number of holes.